Hello everyone, welcome to the session on digital electronics. In this session, we'll be discussing one of the most important type of counter called as the synchronous counters. In this session, we will see what we mean by synchronous counters, and we will also design 2-bit, 3-bit and 4-bit synchronous counters. Friends, as you know that you are viewing this session on my YouTube channel Learn with Prakash Kanade, and subscribe to the channel to see many videos on the subjects of electronics and computer science. So let us start the session with the question what we mean by synchronous counter. Now we know that counter is a logic circuit that can count the input square pulses. So this is a logic circuit which is being frequently needed whenever we go for the design of any digital application. We know that there are two types of the counters. The first counter is being called as the asynchronous counter, and another type of the counter is being called as the synchronous counter. Asynchronous counter is many times called as serial counter or ripple counter, and synchronous counter, they are being called as the parallel counters. We know that in case of synchronous counter, the clock pulse is not simultaneously applied to all the flip-flops, but it is applied only to one flip-flop, and the output of the flip-flop will drive the clock of the next flip-flop. But in case of synchronous counter, since as their name indicate, it is a synchronous, and therefore all flip-flops will get simultaneously applied a clock pulse, and therefore the state of every flip-flop will get changed whenever we apply a clock pulse. And therefore one can easily say that the synchronous counters are faster counters and asynchronous counters are slower counters. But whenever we want to achieve the speed, it means that we will require more hardware. So synchronous counters will require more hardware than that of asynchronous counters. Now, whenever we want to design any synchronous counter, then there are certain steps that need to be followed. In the first step, we will decide how many flip-flops are required. Because if there are only 2 pulses to be counted, then we will require 1 flip-flop. But if there are 4 pulses to be counted, then we will require 2 flip-flops. So in the first step, we need to decide how many flip-flops are required for the counter. Then we need to study the JK truth table, that is the truth table of JK flip-flop. And according to the truth table of the JK flip-flop, we need to prepare one more table, and this table is being called as the transition table. So what is the initial state and what is the next state after the application of the clock pulse? By checking the truth table of the JK flip-flop, we can prepare the transition table of the JK flip-flop. Once the transition table is being prepared, then we will prepare a truth table, and this truth table is different from what we earlier have. So this table is being called as the JK excitation table. And from the transition table, we will go for the JK excitation table. Then we will use the Karnaugh maps, and by using the Karnaugh map, we will simplify the equations for the outputs of each flip-flop. And then finally, we will draw the logic circuit by making the use of these SOP equations. So these are the steps that one need to follow whenever one go for the design of the synchronous counter. So initially decide how many flip-flops are required. Then from the truth table, prepare the transition table. Then from the transition table, prepare the JK excitation table, which is a kind of truth table of the counter. Then use the Karnaugh map and simplify the equations. And then finally draw the logic circuit. So we will go for the design of a 2-bit synchronous counter, and this counter is being called as a modulo 4 counter because this counter can have 4 states. So this counter can count 2 raised to 2, that is 4 pulses, and therefore this counter is being called as a modulo 4 counter. Now whenever we want to count 4 pulses, it means that we will require 2 flip-flops for this counter. Now, initially, we should know what is the JK truth table, and from the JK flip-flop truth table, we can prepare the JK transition table. So this is the truth table of JK flip-flop. When J and K are 0, 0, the output Qn plus 1 will be equal to Qn, that is the initial state. For 1, 0, output will be 1. For 0, 1, output will be 0. And for 1, 1, the output will be complement of the initial state, that is Qn bar. Now, when you know this truth table, then you can prepare the transition table. Now suppose the initial state is 0 and you want to make a transition to 1. Then from this table, we can easily observe that whenever we want the output to be 1, then either j and k must be equal to 1, 0, or if the initial state is already 1 and if it has to remain, if it has to get changed to from 0 to 1, and therefore from the truth table one can easily observe that j and k can also be 1, 1. So these are the two possible applications in order to achieve this transition from 0 to 1. Therefore, we can say that in both the cases, j is equal to 1 and k can be either 0 or 1. And therefore, in the transition table, we will make an entry 1x. So whenever you want to achieve a transition from 0 to 1 of the JK flip-flop, then j must be equal to 1 and k can be anything, either 0 or 1, and therefore we have written x. Now, whenever we want to achieve a transition from 1 to 0, then one can easily observe that from the truth table, this condition can be applied, that is j is equal to 0, k is equal to 1, and then the output is equal to 0. And another possibility is that we need to have a toggle state because 1 is changing to 0, and therefore again we will consider the fourth state of the JK flip-flop truth table where j is equal to 1 and k is equal to 1. And therefore in that case, one can easily observe that the value of k is equal to 1 in both the cases, but the value of j can be either 0 or 1, and therefore in the transition table we make an entry x and 1. So the value of j can be either 0 or 1, but the value of k must be equal to 1. Now whenever there is a transition from 1 to 1, then we need to consider the first two possibilities from the truth table. That is, there is a transition from 1 to 1, so there is no change in the state. So j can be 0, k can be 0. And again, we want the output to be 1, and therefore this case is also possible, 1 and 0. So one can easily observe that in both the cases, k is equal to 0, and therefore we can write j x and k 0. And whenever there is a transition from 0 to 0, then there are two possible cases that either you can have j and k 0, 0, or you can have j 0 and k 1, and therefore in the transition table we will make an entry 0x because in both the cases j is equal to 0 and k can be either 0 or 1, and therefore the transition table entry will be 0x. Now, once you know the transition table, then you can prepare the JK excitation table. So initially when the clock is equal to 0, the present state will be equal to 0, 0. The next state will be 0, 1. And then we will consider what can be the values of J1, K1 and J0, K0. Now, if you look the transition of Q1, then there is a transition of 0 to 0. And therefore from this transition table, for the transition of 0 to 0, we will put J1, K1 is equal to 0x. And if you look for the transition of Q0 from 0 to 1, then you will find that there is an entry of j equal to 1 and k equal to x, and therefore we will write j0 is equal to 1 and k0 is equal to x. Now similarly, when the first clock pulse is applied, the present state will be 0, 1, the next state will be 1, 0. When you check the transition table, then there is a transition of 0 to 1, therefore I will write 1x. And there is a transition of 1 to 0, and therefore I will write x1 in j0, k0 column. When the second clock pulse is applied, the present state will be 1, 0, the next state will be 1, 1. There is a transition of 1 to 1 for Q1, and therefore we will make an entry x0 from this table. And there is a transition of 0 to 1, and therefore we will make an entry 1x for j0, k0. When the third clock pulse is applied, then the present state will be 0, 1, 1, and the next state will be 0, 0. And therefore there is a transition of 1 to 0 for both the flip-flops, and therefore we will make an entry x1, x1 in the columns of j1, k1 and j0, k0. So from this transition table, it is possible that we can prepare the JK excitation table. So JK excitation table, you can say it is a form of truth table for the counter. So look the steps that we have been followed. Initially, we must know what is the truth table of JK flip-flop. From JK flip-flop, we prepare the JK transition table. From transition table, we will go for the excitation table. Now, once the excitation table is prepared, then you can make the use of the Karnaugh map to simplify the SOP equations. Now, I will draw here a Karnaugh map, Q1, Q0. We will make an entries of 1, X and 0. Here you can easily observe that we can form a pair, and therefore we can write an equation that the value of J1 is equal to Q0. Similarly, you can prepare a Karnaugh map for K1 by looking into the column of K1. You can make an entries of 1, X and 0, and you can again form a pair so that you can write the equation K1 is equal to Q0. Now, when you make the entries for the Karnaugh map of J0, you will find that all the blocks have been filled with 1 or X, and therefore there is a quad formation, and therefore we can write the equation J0 is equal to 1. And similarly, we can write the equation K0 is equal to 1. Now, once the equations are ready with you, then you can draw the logic circuit for 2-bit or modulo 4 synchronous counter. So there are 2 flip-flops that are being required. The clock terminal of both the flip-flops is made common, and clock pulse is simultaneously applied to both the flip-flops since it is a synchronous counter. Clear inputs are also made common. Preset inputs are kept at 1. J0, K0 will be kept equal to 1 according to the equations that we have obtained. Then J1 and K1 both will be connected to Q0 according to the equations that we have obtained. So this is a circuit which will work as a synchronous counter, and this counter can count 2 bits or 4 input clock pulses. Now, similarly, we can go for the 3-bit or modulo 8 synchronous counter. A 3-bit synchronous counter can count 8 clock pulses, and therefore it is being called as a modulo 8 counter. This counter will require the 3 flip-flops. Again, the design steps are same, that initially we should know the truth table of JK flip-flop, 00, QN, 101, 010, and 11, complement of the initial state, QN bar. Now, from this truth table, we can prepare the transition table. So transition table will actually tell us how the transition takes place, what is the initial state, what is the next state, and what should be the values of J and K inputs. So whenever there is a transition of 0 to 1, then from this table, one can easily observe that we can make the use of the second row, and we can make the use of the 4th row from this truth table. And therefore we can write the value of J equal to 1 and K is equal to X, because in both the cases, the value of J is 1 and K can be either 0 or 1. And similarly, whenever we have a transition from 1 to 0, we will make an entry X1. For 1 to 1, there will be an entry X0. And from 0 to 0, again, we can make an entry by using this table. So from 0 to 0 means you can make the use of the first row and you can make the use of the third row. And therefore, in both the cases, the value of J is equal to 0. K can be either 0 or 1. And therefore, we will make an entry 0x. Now, once the transition table is ready with you, see that the transition table is a kind of a thing which will not change, isn't it? The JK truth table is a kind of thing which will not change. So once you understand what is the truth table of JK flip-flop and what is, then you can easily prepare the transition table. And once you prepare the transition table, then the only thing that you need to do every time is the preparation of JK excitation table. So whenever the clock is 0, then the present state will be 000, the next state will be 001. After the application of first clock pulse, the present state will be 001, next state will be 010. Then after the second clock pulse, the present state will be 010, the next state will be 011. Then after third clock pulse, the present state will be 011, the next state will be 100. After fourth clock pulse, present state will be 100, next state will be 101. Then after fifth clock pulse, present state will be 101, next state will be 110. After sixth clock pulse, the next state will be 111. And after seventh clock pulse, one can easily observe that now the counting is over because there are already 8 states, and therefore the next state will be 000. Now you can make the entries for the columns J2, K2, J1, K1 and J0, K0 by making the use of this transition table. So one can easily observe that Q2 is making transition from 0 to 0, and therefore for 0 to 0 there is an entry 0x, and therefore I will write for J2, K2 0x. Similarly, for Q1 there is a transition 0 to 0, therefore I will make an entry 0x for J1, K1. And for Q0 there is a transition from 0 to 1, and therefore I will make an entry 1x from this truth table or transition table. So in this way you can make all the entries in the JK excitation table, and once you have made all such entries, then you can prepare the Karnaugh map for each of the J and K columns. Now we can easily prepare the Karnaugh map for J2, J1, J0, K2, K1 and K0. So you have to look into the column of J2 and make an entry of 0, 1 and X. Here you can form one pair. Here you can form one quad. Here you can form an octet. Here again you can form one pair. Here you can form one quad, and here you can form one octet. And therefore we can write the simplified equations. J0 is equal to 1, K0 is equal to 1 because all the variables are reduced. For J1 we will write the equation Q0 because Q0 is equal to 1 for this quad. Similarly for K1 we will write the equation Q0. For J2 we are having only one pair, and therefore our equation will be Q0 into Q1, and similarly for K2 our equation will be Q0 into Q1. Now we can draw the logic circuit by making the use of this equation. So this is our first flip-flop having input J0, K0, and both the inputs are connected to 1 as per these equations. J1, K1 are connected to Q0, and J2, K2 are connected to the output of the AND gate, and the output of the AND gate will be Q0 into Q1. And also observe that the clear terminals of all the flip-flops are made common, and the clock terminal of all the flip-flops are also made common. And the preset is being kept at logic 1. So this is a diagram. If you construct the logic circuit according to this diagram, then this circuit will work as a modulo 8 synchronous counter. That is, this circuit can count 8 clock pulses. Now similarly we can go for the modulo 16 synchronous counter. So this is a counter where we will require the 4 clock pulses because 2 raised to 4 is equal to 16, and this counter can count 16 clock pulses. So for the 4 flip-flops, again we need to prepare the JK transition table. As I told you, the JK truth table will not get changed. The JK transition table will also not get changed. It will remain the same. And as I told you earlier, we can prepare the JK transition table by making the use of this truth table. Now, once you have prepared, then you can easily prepare the JK excitation table. So here there are 4 flip-flops, therefore there are 16 possible states. So for example, the first state is 0000, the next state is 0001. Then after the application of the first clock pulse, the present state will be 0001, the next state will be 0010. And in this way, one can easily observe that after 15th clock pulse, the present state will be 1111 and the next state will be 0000. Now you can make an entries for the columns J3, K3, J2, K2, J1, K1 and J0, K0 by making the use of this transition table. So in the first case, one can easily observe that there is a transition of 0 to 0, and therefore we will make an entry 0x for J3, K3, J2, K2 and J1, K1. Only for J0, K0, we will make a transition table entry as 1x because there is a transition from 0 to 1. So by making use of this table, one can make all such entries carefully. So once you have made all such entries carefully, then you can go for the SOP equations. Now we can go for the simplified SOP equations. So again, you can make the use of the Karnaugh maps, and by making the use of the Karnaugh map, you can obtain the equations such as J0 is equal to 1, K0 is equal to 1, J1 is equal to Q0, K1 is equal to Q0, J2 is equal to Q0, Q1, K2 is equal to Q0, Q1, J3 is equal to Q0, Q1 and Q2, K3 is equal to Q0, Q1 and Q2. And once you obtain such equations, then you can go for constructing the logic circuit. For the logic circuit, you will need 4 flip-flops where J0, K0 is connected to 1, J1, K1 is connected to Q0, J2, K2 is connected to Q0 into Q1, and J3, K3 is connected to Q0, Q1 into Q2. So here we will require 2 AND gates, and the clock terminal is made common. Also, the clear terminal is made common, and the preset terminal is to be kept open. So thank you friends for watching this video. Hopefully you have understood how to design the synchronous counters. In our next session, we will go for some odd synchronous counters. Thank you all for viewing the session.